just said, it's one of those like $7 shirts from Walmart, and I like the design, and the Punisher is my stepdad's favorite, so.
I found a.
Those seem like very good rivalries.
How is everyone today?
Yeah.
What?
For Team Iron.
All 14 of you. Everyone's ready for a break, for sure. So I'll have your exams graded by the end of the weekend.
Captain America.
But we're going to start our last unit today, Chapter 5. There's actually one section from 6-2, but mostly Chapter 5 stuff. Chapter 5 deals with a few different things that we'll see are related. In 5.1, we're going to look at how to approximate an area that's under a curve. In 5.2, we'll look at the definite integral, and we'll see how that's related to the indefinite integral or the antiderivatives that we took in 4.9. And then 5.3 is the fundamental theorem of calculus, which tells us how to evaluate the definite integral from 5.2. And 5.4 is application, where we find the average value of a function. And then 5.5 is the section where we get one technique to find antiderivatives, outside of the ones we already know. And then the one from 6.2, Chapter 6 stuff, is finding the area that's between two curves. So in 5.1, when we're approximating areas under the curve, we're sort of building up to section 5.3, where when we look at a function, Chapter 3 told us that if we take the derivative, we get slopes of tangent lines or instantaneous rates of change. And then in 4.9, we looked at the antiderivative. We haven't yet discussed what that actually tells us. But I believe 5.3, 5.2, 5.3, we sort of get the idea of what, at least one thing that it does for us. So it is a bit of a build-up to kind of interpreting what an antiderivative does, but anyhow, here in this section we're looking at how to approximate areas under a curve. And I guess one physical interpretation of that is if we looked at displacement. And if you remember that displacement is just a change in position, so from time 1 to time 2, displacement is the difference in the positions at time 1 and time 2. So this is just kind of motivating the area under a function discussion. So here, if we have our velocity function graphed, it's constant 60 miles per hour on the first 2 hours. And we were to ask, if we were given this specific situation, what is the displacement here? What is the displacement on that particular situation? So we actually would change position. We're not going to end up where we started at. Because the situation is that we're traveling 60 miles per hour for 2 hours. So how far have we gone? What's the change in position from our starting to our ending?
120 miles.
Yeah, it's 120 miles. So we have, so it's kind of, you know, you're probably looking at that and saying, well, if displacement is defined as a change in position and I don't have a position function, how could I possibly find the change in position, right? And that's a valid question. Here it's a little more straightforward because we can just use reasoning. 120 miles an hour for 2 hours, that's what our displacement is. Displacement is 120 miles per hour for 2 hours. Sorry, 60 miles per hour for 2 hours is 120. But the reason we're kind of looking at this simplistically is because we want to notice that the displacement under this velocity curve, if you want to call it a curve, but under the velocity function, the displacement, it's the same thing as the area under this curve here. So if we look at what's the area between the t-axis and the velocity function, that area is actually 120 as well. So this area, I'll just shade this in. So whatever all of this area is. So we have a height of 60 and a length of 2.
So that could be square miles, right?
No, if we're just talking about displacement,
Okay.
like we would have the miles an hour times the 2 hours, which would cancel out the
Cancel the
hours.
hours, right.
Yeah. Right.
It's just confused with the area, because area is usually,
In square units. Yeah. So the area here though is the same thing, right? Because we have the units of the length or the height is 60 miles per hour times the units of the width. So that's the same thing we see here. So displacement is the area. So displacement is the area. Under the velocity function. On 0, 2. The area, yeah, I guess, and the t-axis. You're not going past the t-axis. So that's just a really straightforward example because we're dealing with a rectangle, a constant velocity. But we could say that this would be evidence enough to suggest that if I have any velocity function and I looked at the area underneath, then that would tell me the change in position. But we know velocity functions aren't as simple as that. So like, what if we had a velocity function like this? And we wanted to know what's the displacement from on the interval from 0 to 2. Is it, yeah, and so then we have to find the area in green, and it's not a nice geometric figure, right? It's not something we can just plug into a formula to figure out. So that's what we're interested in, these more generic shapes or these or some function that's not constant. I think the idea is really straightforward, but it sort of becomes cumbersome and tedious because of all of the notation that's involved. But the idea to find the area here on this velocity function, and we'll say that's 2. We'll say that's 2. Is what now? What'd you say earlier, Zach?
I can't remember the formula, but it's essentially you just break it into intervals. And
Okay.
I can't remember what you do. I just remember you multiply. It's a multiple of 2 and a sum of.
Okay,
intervals.
yeah. So you're thinking of the more technical approach, which is related to what we do is we just break this green area up into manageable pieces, meaning we just look at a bunch of rectangles.
It's almost like a graph, like on Desmos, technically, right? It's essentially breaking the intervals down into, I guess on a more technical term, such small shapes that,
Yeah.
that it literally fits the curve.
Yeah.
You're able to put something that is a square shape. You cut it down small and small and small enough.
Uh-huh.
You can get it to fit.
Right, that's exactly right. And that idea is based on a limit yet again.
Right.
So we'll see here in this chapter, this is like the other pillar of calculus. We had our derivatives, we had our integrals, and holding those two things together was the limits. So we'll see, in a moment, we'll see how a limit actually comes into play when we're trying to find an exact area. But for now, let's just stretch this out. The way we approach this is we're just going to say, whatever, that's straight. We're going to say, break this region up into a bunch of rectangles. So I'm going to say, all right, well, here's some rectangles. So based on how I chop up the x-axis is going to give me these sort of individual rectangles here. So on this interval, I'll have this rectangle. On this interval, I'll have this rectangle, whatever, and so forth. So we just divide the region up into a certain number of rectangles, and then we approximate, or we find the area of each rectangle, and then we just add that up, and that'll give us an approximation of the area. So let's just kind of write it out in words. We're going to divide, or the more technical word is partition. The region in question, I guess. So we're gonna divide up that region into a certain number of subintervals, and we'll just say n. Subintervals. In other words, think when you see subintervals, just think of rectangles into n rectangles.
That's velocity. So
Yeah.
velocity n times 2, you got it.
Yeah.
Right.
Right. Right. So we're gonna partition that region into n rectangles. Compute the area of each rectangle and just for simplicity, we'll keep the widths of each or the bases of the rectangles all the same. We'll see as we go along that they don't all have to be the same. Because what we're trying to do is get an exact area. We're eventually moving away from an approximation, but the idea of the exact area is based on how we approximate the area. So how would we compute the area of this first rectangle? If we say this base has some, we'll just call it length. And since that's the first rectangle, we'll just call that the length of the first rectangle.
Velocity of L over 2.
Yeah, and the height of each rectangle, notice the height of this first rectangle is given by this height right here, but that height right there is solely coming from the function value. So the area of each rectangle, we'll just say for now this is the length times the height, which is the length times velocity at some t value, right? That's some value of t. We plug that into the velocity function, it gives us that point or that y value, which is the height of that rectangle.
Do you not do it at the midpoint?
Yeah, there's various. What we'll focus on is either the left, right, or the midpoint.
Okay.
But as we'll see, it doesn't matter. You can actually take any point. You can take any t value in that first rectangle and use that to evaluate the height, as long as we're approximating.
Okay.
When we make that exact, we'll see it's not going to matter which one we choose, because as you said, you got to put more and more in.
Right.
Yeah.
Okay.
So to compute the area of each rectangle, then sum all of the areas up. This will give us an approximation. Of the area under the curve. And so I think maybe even intuitively at this point, how would we make that area exact? What would be necessary to find an exact area?
Your L would have to go towards 0.
Right. So
You'd
like
have to
the
add
length.
more and more like rectangles and make their width shorter and shorter and shorter.
Yeah.
That way you get more rectangles
More
with
rectangles.
less deviation over the function
Right.
itself.
Right.
And also, I have a question. So this is
Sure.
an over approximation. What are they called normally? So like if there's an under approximation and an over.
Well, let's not worry about like what stuff's called at this point, because I think if we start, it's good that we're thinking ahead, especially if you've seen this before. But we will address all of that. I just don't want to start like confusing
Oh yeah.
terminology and processes. But yeah, the idea is that's an approximation because I'm using 1, 2, 3, 4, 5, 6, 7. I'm only using 7 rectangles to approximate that area. The more and more rectangles I put in there, the better and better that approximation is going to be. Okay, so let's look at an actual example. We've got a velocity function as t squared on the interval 0 to 8. And we want to approximate the displacement again, which is just the area under the velocity curve, by partitioning or dividing the interval 0, 8 into the following number of subintervals. And again, number of subintervals, think about that as the number of rectangles. The first couple of ones we'll draw out, but then this is, after we kind of draw this out and see what's going on, this is sort of when the notation gets really tedious. Because if I wanted this problem with 2 subintervals, then you just got to draw 2 rectangles, right? If I wanted 10, then you just draw 10 rectangles. But what if I wanted to use 50 or 100 rectangles? It's highly inefficient to draw this function out and then draw 100 rectangles and to see what all you're using. So we do want to make concise notation out of what we're talking about here. But for now, let's just look at the velocity function. And we'll say that's 8 right there. So v of t is t squared on the interval from 0 to 8. And we want to divide the region 0 to 8. We want to divide that up into put 2 partitions in there. We want 2 rectangles in that entire region. So the first rectangle then has to go from 0 to 4. And then the second rectangle will go from 4 to 8. Yeah.
Would it, just to clarify, sorry, as of right now, they're going to be equal intervals, but as
Yes.
we progress. So the reason that it's from 0 to 4 is because right now we're just focusing on even intervals.
Yeah, where we want to look at equal bases of each rectangle.
Okay.
maybe I'll scoot that over just a little. So then, if we draw this rectangle, you know, like, do I use, like, there's multiple options here. The base of this rectangle, that's fine, it's just 4. But what do we want to use for the height of the rectangle? That has to be specified as well, and that's specified, it says use the midpoint for the height of each rectangle. So what we're going to do to determine the height of this first rectangle is say, well, what's the midpoint between 0 and 4? So we're going to use that t value and evaluate the function at 2. That y value right there is going to be the height of that rectangle. So that's the rectangle we're using. I'm going to erase this. In that first region.
So it'd be 2 squared?
Yeah, right, yeah, that's how high that rectangle will be. The second rectangle from 4 to 8, again, we're going to use the midpoint 6 to determine its height. So we go up to the function at 6, and we use that function value to determine that rectangle's height.
So even if we're not given the y value, the height is equal to the velocity.
Yeah, the
or
function.
T or, you know,
Yeah.
x, whatever that displacement may be.
Yeah.
Okay.
Yep. So, but if I said use the right endpoint, that would change the height of the rectangle.
Right.
If I said use the left endpoint, that would also change the height of the rectangle. So at this point, it doesn't matter what you use. Using 2 rectangles to approximate this area is going to be pretty crummy.
I mean, generally speaking, though, h is equal to the velocity at the x point.
Yeah.
Whatever that x point may be.
Right.
So we can just say that's pretty, like, standard
It
across
is.
the board.
Yep. The height of each rectangle is the function evaluated at some value in that rectangle.
Right, whatever the
Right.
x may be, or the do
Yeah.
midpoint, endpoint,
And-
start point, whatever
right.
it may be. Okay.
Exactly. Yeah. Just in general, the height of the rectangle is f of x.
Okay.
Okay, so that's the height of this rectangle here. I guess I should have used a different color. And so we've got 2 rectangles approximating the area. And our drawing is not terribly accurate, but you can see that it's a pretty terrible approximation because the left upper corner of the first rectangle is over the area. The right corner is under. The second rectangle, we've got a piece poking out, and this area up here in the top right of the function not even being accounted for by those rectangles. So we're just getting a sort of basic idea. So the area, we'll just say is approximately the area of the first rectangle plus the area of the second rectangle. And the area of the first rectangle is just the width of the base, which is 4, multiplied by its height, which we said was v of 2, plus the width of the second rectangle, also 4, times the height of the rectangle, which was v of 6. Is everyone okay with that? Are there any questions or comments or clarity needed here? Yeah.
Is the second 4 from 4 to 8?
Yeah, the second 4 is this 4 to 8, correct. So we can draw these out too. Let's look at these. This is the first rectangle, and this is the second rectangle. And this height, v of 2, this height v of 6. Okay, so that's 4 times v of 2. Our function again was t squared, so that's 2 squared plus 4 times v of 6, which is 6 squared. So we have, what do we have? 4 times 8, 4 times 4, 16 plus 36 times 4. There's 160. Do we have that? So we say the area under that curve is approximately 160. Based on two rectangles, 2 subintervals. Does anyone have any questions on that? Okay, same situation using 4 rectangles instead of 2. So we're going to split the interval 0 to 8 into 4 pieces, 4 equal pieces. So we go from 0 to 2, 2 to 4, 4 to 6, and then 6 to 8. In each individual rectangle, we'll mark with different colors their bases. Again, we're using the midpoint of each interval 0, 2, 2 to 4, 4 to 6, 6 to 8 to determine the height. Chris, did you have a question?
I don't know.
Okay. All right, so then we've got the length of each rectangle, which is all of them are 2. The height of the first rectangle is coming from the midpoint into the function. So we're plugging 1 into t squared to get the height. Two to 4, we're going to use 3 in the function to get the height of that rectangle. Then 5, the height of the third rectangle. And then 7. So again, we'll just write it here. Area is approximately the area of the first triangle, rectangle rather, plus the second, plus the third, plus the fourth. So we're using 4 subintervals, gives us 4 rectangles. So it's 4 individual areas to look at. The lengths 2 for all of them. The heights of each rectangle is what varies or what changes. So the height of the first rectangle was V evaluated at 1. Height of the second, V evaluated at 3. Third was V evaluated at 5. And the fourth, V evaluated at 7. Oh man. We have to add all that up. Everyone okay with this? Okay, so then we've got 2 times 1 squared plus 2 times 3 squared plus 2 times 5 squared, and times 2 plus 2 times 7 squared. So whatever that is. Anybody have a calculator? 168. Thank you. So we went from an approximate area using 2 rectangles of 160 to 168 using 4 rectangles. See the exact area, just for comparison, the exact area is 170.6 repeating. So we used 4 rectangles. We got pretty close for using 4 rectangles of the overall area. And again, the idea is that if we wanted an exact area, then we just put more rectangles in, right? We could do the same process using 10 rectangles and 20 and 30 and 40 and so on. But you see, it starts to get a little bit tedious to draw all that out, especially if we have to use 50 or 100 different rectangles. So here's the, I guess I could have just looked at this table, but here's kind of the situation. The same curve from 0 to 8 with 64 rectangles kind of looks like this. We computed these two. We used n equal to 2, and then we used n equal to 4. But we could have kept going. And as we keep going, as we keep using more and more rectangles, we see that this approximate area gets closer and closer to the actual area. So ultimately what we're going to do to find an exact area was we're going to let the number of rectangles we put in that region go to infinity. And I'll just put this here, put an infinite number of rectangles in the region. I don't know, that's fine enough. But I mean, you can't put infinitely many things in something, right? So really what that means for us is we're computing the limit as the number of rectangles approaches infinity. For an exact area. Okay, do y'all have any questions before we move on to the tedious notation? Just keep in mind that this is all you're doing. At the end of the day, what we just did with 2 and 4, that's all you're ever doing. And then we're eventually going to let that go to infinity.
I was just wondering how would we involve n into that function? I mean, just the function we just did. If you want to process for that.
Yeah, so it's actually
I mean, if it's possible.
yeah, it is possible. At this point, we can just say that there is going to be a thing where we use n, and we'll see that in just a minute. But that n is going to approach infinity to give us an exact value or exact area. Okay. So where that actually shows up is if we just take a more generic approach. And we say, all right, here's some curve. What's the area of R? And we're going to split that region up into a certain number of partitions. We'll just call that n. From A to B. And A will be this, we'll call that x sub 0. B will be called x sub n. So n is 2 in that last example, then n was 4, right? So we had 0 to 8. This was x sub 0, this is x sub 1, this was x sub 2. That's 2 rectangles. This was x sub 0, 1, 2, 3, 4. That gives us 4 rectangles. We're just making this a lot more generic. Oops. So for each one of these x sub 1, 2, 0, etc., those are going to be called grid points. They're basically just the boundary of each rectangle. What x value gives you the boundary of each one of your rectangles. Those are called grid points. And we have these subintervals. The first subinterval goes from x sub 0 to x sub 1. That's the length of the first rectangle. The second subinterval, the second rectangle, goes from x1 to x2. And so on and so on. The nth rectangle goes from x sub n minus 1 to x sub n. Or, if it was the 100th rectangle, that would be x sub 99 to x sub 100. The value we plug into the function to determine each rectangle's height will be denoted here as x star sub k. So like x star sub 1 is the x value in the first subinterval that we plug into the function to get its height. X star sub 2 will be the value in the second rectangle we plug in to get its height, and so forth. So in general, this x star sub n just means what x value at the nth rectangle do we plug in to get that particular height of that particular rectangle. Does that make sense? Like if I'm out here between this x value and this x value, if my function's doing that, I have to plug some x value in between those two. I have to plug one of those x values in to get the height of the rectangle. And that's all that x star is. So that's just the notation that this textbook uses. Other textbooks are going to use similar notation. And so the definition of a regular partition then is, suppose the interval AB, for us, that example, it was 0 to 8. We're partitioning that into n subintervals or rectangles. It's not technically a rectangle, but I think it's helpful to think of those subintervals as rectangles. So this, like we said, this x sub 0 to x sub 1, that's your first rectangle. More specifically, it's the base of the first rectangle. And then this is your second and third and fourth and so on and so forth. So we're putting that number in rectangles in this interval of equal length, which we're going to call delta x, just for some change of x. And the length of each rectangle, delta x, is defined as b minus a over n. In other words, it's the total length from 0 to 8, let's say, divided by how many rectangles you put in. So b minus a is the total length of that interval, and then we have to divide that by the actual number of rectangles we're placing. The endpoints, the boundaries of each rectangle, are called the grid points, and they create a regular partition on the interval AB. And in general, the kth grid point is given by this formula: x sub k is a plus k times delta x for k equals 0 all the way to n. So this x sub k gives us the boundary of each rectangle, which gives us each subinterval. And so just to solidify this notation actually works and kind of how it works, we're going to go back to the one we just computed, the velocity t squared on 0 to 8 with n equal to 4. And instead of drawing that out, we're just gonna follow this process that's here in this definition to see that we do actually come up with the same values for the endpoints of our rectangle. Okay, so the first thing we want to do is find delta x, and delta x is simply b minus a, the total length of the interval, divided by the number of rectangles you're putting in there. That's, again, delta x is the length of each rectangle. Okay, so on 0, 8, that's our interval. That's a is 0 and b is 8. Since we're using 4 subintervals or 4 rectangles, n is equal to 4. So delta x is 8 minus 0 all over 4, which is 2. And that's the, we'll just write it here again, that's the length of each rectangle. And then, of course, we could verify that when we drew this out, that the length of each rectangle was indeed 2. And then the next thing we could do is find the grid points, which were defined as x sub k. And notice there's an x sub k and then there's an x star sub k. So there's 2 different x's that have subscripts. The x sub k by itself is the endpoints of each rectangle. The x star is the x value in that rectangle we use to determine the height. But we're finding the endpoints of each rectangle as a plus k times delta x, when k ranges from 0 to n, but ours is ranging from 0 to 4 because our n is 4. Our x sub k's will be defined as a, and again, the a is just the starting value of that interval. Our a was 0 plus k times our delta x, which was 2. So the grid points in this particular situation are all defined as x sub k equals 0 plus 2k, where k ranges from 0 to 4. So this thing we're computing here, in effect, is, at the time being, it's a function of k, because k is the thing that changes. So we have, let me do it this way. We have x sub 0 is equal to 2 times 0. Is that clear on how we're doing that? K starts at 0, then it's 1, then it's 2, then it's 3, then it's 4. X sub 1 is 2 times 1. Which is 2. X sub 2 is 2 times 2. X sub 3 is 2 times 3. And x sub 4 is 2 times 4, which is 8. So remember, those are our grid points. Those are the endpoints of each rectangle. So if we put this together, then we say that our partition is going to look like 0 to 2 is the first one. And then the second one goes from 2 to 4. And then from 4 to 6. And then from 6 to 8. So it seems like a lot of work to get what we drew out pretty quickly and pretty simply, right? You could clearly see that each rectangle had a length of 2. And we could clearly see that if I divide 0 to 8 into 4 different subintervals, that each one had a length of 2. I go from 0 to 2, 2 to 4, 4 to 6, 6 to 8. And that was pretty straightforward, just drawing that out, right? We see that solidified here. The first rectangle, 0 to 2, second goes to 2 to 4, right? It's a lot more straightforward to draw that out, but the whole point is we don't want approximations. We don't want to use just 4 or 5 or 10 rectangles. We want to use 100 or 1,000. And then I think at that point, it becomes highly inefficient to draw something out on such a large scale that you can actually fit 1,000 things on your piece of paper to see where each one starts and stops. So anyways, we're just using that definition to figure out kind of what we're dealing with. Whenever we're given an n and an interval, we can find the length of each rectangle and the subintervals through the following definition. Okay, so that was just one specific example. Do y'all have any questions on that? So I'm just going to redraw this once more. All right then. If the interval 1, 9 is partitioned into 4 subintervals of equal length, what is delta x and what are the grid points? So rewrite this formula. Delta x is b minus a over n, and our grid points are just the x sub k's. And x sub k is defined as a plus k times delta x for k equals 0 to n. Okay, so we're on the interval from 1 to 9, so that's our a, that's our b. 1 is a. 9 is b. So delta x is 9 minus 1 divided by n. What's our n? 4. Yeah, 4 subintervals, 4 rectangles, n equals 4. So the number of subintervals, the number of rectangles is always n. Those, I guess they're like 3 different words to describe the number of rectangles. So we have 8 over 4. So the length of each rectangle is 2, delta x. And then we can find the endpoints of each one of those 4 rectangles by finding the grid points, x sub k. And our x sub k then is a, and our a is 1. So our x sub k is 1 plus delta x times k. Remember, this is kind of like a function of k, so if we want to think about it, our inputs here. And k ranges from 0 to 4. again, 4 rectangles. So we have x sub 0, our first grid point. X sub 0 is 1 plus 2 times 0. Which is 1. Keep going here. X sub 2, or sorry, 1 rather, x sub 1 is 1 plus 2 times 1. So the second grid point is 3. Next grid point is x sub 2, which is 1 plus 2 times 2. And that gives us 5. X sub 3 is 1 plus 2 times 3. Which is 7. And finally our x sub 4, 1 plus 2 times 4, which is 9. So that means the partition of 1, 9 using 4 rectangles is 1 to 3 for the first rectangle, 3 to 5 for the second, 5 to 7 for the third, and 7 to 9 for the fourth. Yeah, we could have just drawn that out. There's only 4. It wouldn't be that difficult to draw those out. If you want to draw it out just to verify that the length of each rectangle is 2, the first one is from 1 to 3, the second one is 3 to 5, then you can do that. So I hope the idea of what we're doing isn't terribly difficult. I think it's actually pretty intuitive. It's just when we start adding this notation to it, it tends to muddy things up a little bit. Does anyone have any questions on what we've done? So in summary, we have the areas approximately area 1 plus area 2 plus area n, however many rectangles we're using. And that's the length 1 times height plus length 2 times height 2 plus so on and so forth, length n, height n. But the length of each rectangle is for us, it's always just going to be denoted by that change in x, delta x. The height of each rectangle is simply the function evaluated at some x value in that first rectangle. So how do I want to say this? So the things that give us the heights are the x stars. Since it's in the first rectangle, it's going to be x star sub 1. Plus again, the area of rectangle number 2 is the length, delta x, times the height, which is f evaluated at x star sub 2, since we're using the second rectangle, and so on. all the way to the nth rectangle, where again, the length is delta x, and the height is f of x star sub n. So does anyone have any questions at this point? Even writing these sums out is tedious, right? Like if I had 50 rectangles, writing out 50 different sums is time consuming in and of itself. So what we're going to look at in 5.1 and a little bit later is a more compact way to write out a sum. So this idea that we're talking about, how to approximate an area, is called a Riemann sum. Some guy's last name. And so we're just going to redefine the area in that sense. We're going to say, suppose we've got a function on a closed interval AB divided into n subintervals of equal length. So this is delta x. Then we're going to say if x star sub k is any point in the kth interval or the kth rectangle for k equals 1, 2, 3 all the way to n, then the area is approximately, just put this here, that the area is approximately this sum right here that we just wrote out. And so now we have a specific name for that sum, first length times first height plus second length times second height, et cetera, et cetera. We're just going to call that a Riemann sum. And we get three main Riemann sums. So the one we used to evaluate t squared on 0, 8 was the midpoint, because we took the midpoint between within each rectangle. So we actually use that midpoint Riemann sum for those first two numerical examples. The other two are the right Riemann sum and the left Riemann sum, where you actually just use the left or the right boundary of each rectangle to determine the height. So those are all here. Figure 5.9 is for the left Riemann sum. So you see within whatever interval we are, like if we're looking at this interval, subinterval rather, and we're going to say to determine this particular rectangle's height, I'm going to use the left endpoint of that rectangle. So here's the left endpoint, and I go up to the function. That function value is going to determine that rectangle's height for all of them. If I'm within this rectangle here, left endpoint to determine that rectangle's height. The right Riemann sum is figure 5.10 here in the middle. Whatever rectangle I'm looking at, I'm going to use the right endpoint to determine its height. The right endpoint here of this rectangle, the right endpoint here of all of them is what we're using to get that rectangle's height. And then the midpoint we've seen. So there's the midpoint. I'm going to use that to get each rectangle's height. Does everybody see that? It doesn't, in practice, it doesn't matter if we use the left, right, or the midpoint. As long as we're talking about an exact area, they're all the same. In fact, I don't have to use just the left or the right or the midpoint. I could actually say any x value in that first rectangle I can use to determine the height. And any x value in the second rectangle I'll use to determine the height of the second rectangle and so forth.
Can't you just shorten that process up by lowering your value of n?
You mean like using...
Like if it says, break it into 6 subintervals, I'm like, I don't want to do 6. How about I do like 3? So I do n equals 2 instead. And then at that point, like in the last example, I would just evaluate x at 0, x at 3, and x at 6. Would that still work as, it wouldn't be as long.
Right.
Or, I wouldn't have the full like 0 to pi over 12 and then pi to 12. I'd have 0 to pi over 4 and then pi over 4 to pi over 2.
Yeah, so
Just have your-
what that would affect is your approximation, because if you're gonna use, if you're.
Less accurate.
Yeah, if you're gonna use less rectangles, that means you're gonna be
Okay.
less accurate.
Makes sense.
Yeah.
Okay.
So if it says like approximate using 6 rectangles, there is a definite number associated with using 6 rectangles versus 3 rectangles.
Okay,
6 was obviously better.
right.
But as far as like computations and your homework and stuff, if they say use 6 and you use 3, you know, it's gonna be, it's not gonna count it right because it's 2 different numbers. So yeah, we eventually move away from this process altogether, and you know, it's kind of like doing derivatives. Doing the derivatives by hand using the limit definition is super tedious. So it's like, is there a shortcut? Yeah, there's a shortcut, but we don't look at that until 5.3-ish. Okay. So let the region R be between sine x and the x-axis from 0 to pi over 2. Approximate the area using left, right, and midpoint Riemann sums using 6 subintervals. Again, we're using 6 subintervals. If you want to just draw that region out from 0 to pi over 2, divide it in 6, and see what you're dealing with, feel free to do that. I promise you that's going to be a terrible way to do it when we start using, you know, 20, 30, 50, 100 subintervals, though. So the right, left, and midpoint Riemann sum, the thing that is consistent between all of those is the length of each subinterval, delta x, and the boundaries of each rectangle. So before we even compute left, right, and midpoint Riemann sums, we're going to find delta x. And then we're going to find or list out the partitions. Secondly, we're going to list the grid points. Those were our x sub k's. So what would our delta x be here?
It's pi over 12.
Yeah, pi over 12. Remember, delta x is the length of the interval, so that's pi over 2 minus 0 divided by the number of subintervals. So pi over 2 minus 0 divided by 6 gives us pi over 12. And we need delta x first if we're going to find the grid points, because the grid points also involve a delta x. So we find the delta x first, and then we can list out the grid points. So delta x, pi over 12. Shift this down a little bit. Our grid points, x sub k, are the a. What's our a? 0 plus delta x times k. So we have plus pi over 12 times k. And where does k range from? 0 to 6. So let's just figure out what all of our grid points are. The first grid point is x sub 0, so that's 0 times pi over 12. Remember, the x sub 0 is always the starting point of your interval, and the x sub n, here the x sub 6, will be the ending point. So that x sub 6 should be equal to pi over 6, because that's where we're stopping. Okay. X sub 0 is 0, x sub 1 is equal to pi over 12 times 1. X sub 2 is pi over 12 times 2. Oh, let me do this here. So we have 2 pi over 12 or pi over 6. X sub 3 is pi over 12 times 3. And that's equal to pi over 4. X sub 4 is pi over 12 times 4. Which is pi over 3. We have pi over 12 times 5 for X sub 5. And then finally our X sub 6 is pi over 12 times 6, which is pi over 2. So then we're just piecing those together. The partition that we form on the interval from 0 to pi over 2 we go, our first grid point is 0, so we go from 0 to pi over 12. Then we go from pi over 12 to pi over 6. And then pi over 6 to pi over 4. Pi over 4 to pi over 3. Pi over 3 to 5 pi over 12. And then pi over 12 to pi over 2. Sorry, 5 pi over 12 to pi over 2. If you were, I guess if you were drawing this out by hand, you would have had that done by now as well. But we're going to take these partitions. These partitions and that delta x are the same for the left, for the right, and for the midpoint Riemann sums. So that was kind of like that. All of that stuff was just our pre-work to compute the left, right, and Riemann sums. So part A was using the right Riemann sum. So which of these values are we taking to compute a right Riemann sum? the right values of each partition. So this 0, the pi over 12, the pi over 6. Sorry, that's the left. My bad. Oops. What happened? Oh. Okay. Let's see if I can. All right. Pi over 12, pi over 6, pi over 4, pi over 3, 5 pi over 12, and pi over 2. These are your x stars sub k. So those values that we've circled are what we need to plug into the function to get the height of each rectangle if we're using the right Riemann sum. What's the length of each rectangle? Yeah. The length of each rectangle is always pi over 12 for this particular problem. But we should also say that our x star sub k's, these are what we're using for those, but these are also kind of related to our height. So those two things are all we need. We've got the function. Our function is sine x, and we've got each value to plug in to the sine of x. Okay, so then the right Riemann sum. I'll just put a subscript r here. I don't think this is standard notation, but just for the area using the right Riemann sum is approximately the area of the first rectangle which is pi over 12 times the height of the first rectangle let me write it this way. Pi over 12 was our first endpoint. So that's the pi over 12 times f evaluated at pi over 6. That's the length of the rectangle times the height of the first rectangle. Of the second rectangle times the height of the second rectangle is pi over 12 times f evaluated at, sorry, that should have been pi over 12. I looked at the wrong thing. The second one is pi over 6. First one's pi over 12. So that's the area of the second rectangle and so on and so forth. Pi over 12 times f of pi over 4 is the area of the third rectangle. Pi over 12 times f evaluated at pi over 3. Height of the fourth rectangle. I might not be able to fit this in. I'm just going to write it down here. Pi over 12. That's the height of the fifth rectangle, or the area of the fifth rectangle. Pi over 12 times f of 5 pi over 12. And the height of the sixth rectangle is f of pi over 2 times its length, pi over 12. And really we can see that the delta x is involved with every term. So you could just leave the delta x out, sum up the function values, and then multiply by delta x. It might take a little less time to write all that down if you're just writing it once. And so this is pi over 12 times the sine. F of x is sine of x, so this f of pi over 12 is the sine of pi over 12. Plus all of that other stuff. So that's our approximation to the area under the sine graph from 0 to pi over 2 using right Riemann sums. I know that's kind of time consuming. Are there any questions on what we've done there? So just want, again, make sure your calculator's in radians when you compute these values, not degrees. And so we have that you should come out with the area of the right Riemann sum, using the right Riemann sum rather, to be approximately pi over 12 times all of that, which is 1.125. I used this example from your textbook just so I could steal their image. Maybe I can't steal their image. So there's a visual image of what we've computed. I know it's not anything spectacular considering the amount of work we had to put in to do that, but this is what we've calculated. So depending on the function, sometimes you get an over approximation using the right Riemann sum. Sometimes you can get an under approximation using the right Riemann sum. But here, visually, clearly see that it's an over approximation of the area. Any questions at this point? All right, we'll take a break and then keep on going.